Okay, so where we had left off. So we had light, right? So we had shown that for the most part, light behaves like a wave. We had shown that with our little video, and so you should watch that video if you didn't. On the other hand, though, we can't explain all of the behaviors of light in terms of wave-like properties. We also have to kind of invoke a particle-like nature. So particle-like nature when it comes to energy, right? So Einstein had shown that the energy of light is proportional to its frequency, right? So energy is proportional to the frequency, has nothing to do with the amplitude, which would be very much wave-like. And so this energy is kind of delivered in little packets that he called photons or quanta, okay? Okay, so we'd also talked about matter. We kind of briefly talked about matter with respect to emission spectrums. So emission spectra of various elements, right? So with emission spectra, if you go and excite an element, either via like electrical excitation or heat, they tend to give off these very characteristic colors. They tend to glow these very characteristic colors. And then when you take that color that they're glowing, you pass it through something called a spectroscope. It essentially kind of takes out all the various components or factors out the various components of that color, and you get what's called an emission spectra, right? And so these emission spectra are very discrete spectra, right? So there are just essentially patches of black with very sharp discrete lines at very specific wavelengths. And again, these emission spectra are characteristic of the element that are producing them, right? So the emission spectra for hydrogen, especially in the ultraviolet visible region, is like 4 lines, right? And so if you were to take hydrogen from any source and you were to do the exact same thing, excite it, pass the light that it's glowing through a spectroscope, you would always get this exact same 4 sharp line emission spectra, okay? All right, so then we talked kind of briefly about how the student named Rydberg had modeled the hydrogen emission spectra, but he hadn't been able to explain why his model worked. And then we were left with this guy named Niels Bohr. All right, and so Bohr had attempted to explain what we are seeing with respect to this idea, this Bohr model of the atom, where we had our nucleus, and around our nucleus was our electrons. But the big thing about Bohr was that he thought, okay, our electron can only be orbiting at very fixed radii away from the nucleus, right? So he thought the electron could be a certain distance away or a certain other distance away, right? So these radii differed with respect to they were farther from the nucleus than one another. But they could only be there, right? So they could only be in this radius or in this radius orbiting, and they couldn't be in between anywhere, okay? And so he had given these guys these like numbers, and we'll see what these numbers correlate to in a second. And the big idea behind Bohr was not, these guys weren't giving off light because they were orbiting. Instead, while we were seeing these emissions or these absorptions of light was due to transitions between these various radii, right? So if we had an electron in a higher radii fall down into a lower radius, right, then we would see emission of light of that essentially energy, right? And so whatever that difference in energy was between the two various radii, we would see that energy difference be emitted in a photon of light, right? And so this is why we were getting these emission spectrums. So Bohr himself could not quite explain why these electrons, because he imagined that they were orbiting the nucleus like the planets orbit the sun, why they weren't continuously giving off white light. So he called this like a peculiar mechanical stability that he couldn't quite explain. But again, this idea behind transitions between these orbits or between these various radiuses being responsible for these emission spectra was kind of big at the time, okay? So that's where we were left with. We still couldn't explain everything, okay? So now we're going to move on to this dude named Louis de Broglie, and he's going to give us kind of this idea that if we go back to this idea behind light, right? So light is majority of the time wave-like, right? It behaves like a wave. But when we look at energy, light has a very particle-like nature. So de Broglie took that idea and said, well, what if we turn that around on particles, right? So what if particles are particle-like, or electrons. That's the big one, not necessarily particles. So what if electrons, for the majority of the time, are particle-like? So particle-like. But maybe what if they also have wave-like properties as well? All right, so what if they behave like a wave as well? What if they have a wavelength to them? Okay, and so he kind of hypothesized this equation. This is called the de Broglie equation. And in this equation, what he said was the wavelength of an electron, or the wavelength of anything, really, is equal to h, which was, again, Planck's constant. So this is 6.626 times 10 to the minus 34th joule times seconds. So it's Planck's constant divided by m here is mass of whatever thing we're looking at, and then v here is velocity. Okay, so this isn't v, or this isn't nu. It's not nu. This is v for velocity. Okay. Again, nu is frequency, just to remind you. They look very similar. Okay, so that was the big thing, right? Okay, so maybe all things have wavelengths, right? Maybe all things behave like waves. The part in time, or the region of time, the region of space, or something like that, where this actually becomes important, like something having a wavelength, is when the wavelength itself is proportional to the size of the wavelength that it's representing. And I know that doesn't really make any sense, but if we take something like a baseball, right? So a baseball is really big, right? And so if we plug in all of the various parts of the baseball into this de Broglie equation, what we will get is a wavelength that's incredibly small. By small, I mean like 10 to the minus 34th, like meters, like really, really, really big, especially compared to the size of the thing that this wavelength is for, right? So because of that, the wave of the baseball doesn't actually play, you don't see it, like it's not there. It doesn't behave like a wave, right? Now, the only time that this wavelength actually starts to manifest itself in these various properties is when it's actually comparable to the size of the thing that it is a wavelength for, right? So, for example, an electron is itself incredibly small. So when you plug all of the various things into our equation here for the electron, we'll get wavelengths on the order of like 10 to the minus 10th, right? Which is actually very comparable to the size of the electron itself, okay? So things don't actually start behaving or manifesting their wave-like nature until they are actually on the order with respect to their actual wavelength, okay? Okay, so where would you actually need to use this de Broglie equation to calculate the wavelength? So let's say that we had a problem where I wanted to know the velocity of an electron that has a de Broglie wavelength of about 1.2 times 10 to the minus 10th. So how would I go about doing that? I would use my little de Broglie equation. So wavelength is equal to h over mass times velocity. And I would go ahead and solve for velocity here, because again, that's what we're looking for. So to do that, I would multiply both sides by mass times velocity. So that would give me mass, velocity, wavelength is equal to h. And then I would go ahead and divide both sides by mass times wavelength. And so that would give me velocity is equal to h over m times wavelength. And then I would go ahead and plug everything in. So 6.626 times 10 to the minus 34th. This is joule seconds all over the mass of the electron. This is like a constant. It's 9.1 times 10 to the minus 31 kilograms. And note you have to use kilograms here because, again, of joules. So 9.1 times 10 to the minus 31st kilograms times the wavelength of the electron, which is 1.2 times 10 to the minus 10th meters. Okay, so when you do that, you end up getting something like 6.1. Let's do that for real. Velocity is 6.1 times 10 to the 6th. Then you end up in units of meters per second. So this is a point, 6 point. So when you look over here, you find, oh, look, here it is. So the electron is moving very, very, very fast. So things that are very small, moving very fast, have wavelengths that are comparable to the size of the actual thing. Okay, so that's great. So de Broglie can say, hey, what if all things have wavelengths correlating to them, right, corresponding to them? But how do we actually prove that, right? So how do we prove that the electron has a wave-like nature? It has a wavelength that manifests itself. So kind of proof of this idea, this wave-like nature of the electron, came a few years later in the following experiment. Okay, so right now, if you want a nice little video that kind of explains this better than I do, I would go ahead and stop this, and I would go to the Blackboard site and click on the video, the Dr. Quantum electron diffraction video, because that's going to explain this much better than what I can do right now. But I will try as well. Okay, so go do that. If you're not, then stick with me, and I will explain exactly what happens in this experiment. Okay, so let's imagine we had a source of electrons, right? So we have some sort of electron source, and we are shooting them at a barrier, right? So we have a barrier here, and it has two tiny slits in it, right? And these two tiny slits are fairly close to one another, right? So again, the majority of the time we think of electrons being these tiny little particles, or like in the video they say tiny little marbles, right? And so if you take tiny little marbles and you shoot it at a barrier with two slits, what you would expect to see is the tiny little particles essentially coming through the slits where they're at, right, and landing right directly behind the slits on the screen behind them, right? You would expect particles to just go through wherever the slits were and end up right behind where the actual slits were on the barrier. Okay, again, that's what you would expect with electrons, which we think of as particles. What you actually get, though, with electrons is something different. So if you were to take an electron source and shoot electrons at a barrier with two slits, instead of getting the two, essentially two beams that correlate to the two slits, what you get is an interference pattern, which is very characteristic of a wave, right? Because waves diffract and they also interfere with one another. Okay, so this is a thing, like this is an issue. Like you're shooting particles at a barrier and you're getting an interference pattern. How could that possibly be? So scientists thought, well, maybe the electrons are going through and they're like diffracting off one another, right? And so we're getting this various thing. So they're like, okay, well, let's slow our electron source down so that it only shoots one electron at a time. And so they do that and they wait, right? Because if they're only shooting one electron at a time, it's only going to show up as one dot at a time on the slit, or the photographic film behind, right, where they're actually seeing these guys end up. So they wait, and over time, as it passes, what they end up getting long term is, again, this interference pattern, right? So the problem with this is that you have an electron going one at a time. If you want to think of it as a particle, which people still want to think of it as a particle, you think, oh, it has to only be going through one slit. It can't be going through both, right? So that's the problem, right? How is it, if it's going through one slit, how does it make an interference pattern on the screen behind, okay? So, again, scientists wanted to figure out, well, it can't be going through both slits, right? So let's look and see which slit it's actually going through and see what we can make of that. So they do that, okay? And when they do that, they, again, have single electrons hitting the barrier one at a time, or going through the slits, and they see, oh, here's the electron, oh, here's the electron, right? So they're coming through, they actually see where they end up, but what that does is it essentially collapses the interference pattern, and it produces the type of pattern that you would expect just for particles going through the slit, right? So when you try to measure the position, or which slit the electrons are actually going through, the electron behaves like a particle, right? When you don't try to measure the position, when you don't know anything about the position of the electron, and instead just let it go through, then you get the interference pattern, which is part of its wave-like nature, okay? So this is kind of like the trade-off with respect to the electron, right? We've been asking this question, well, where is the electron at? What is it doing? How do we know? Well, in the end, what we can know about the electron is there are particle-like properties to it, and there are also wave-like properties to it. And it's going to behave as a particle or as a wave, depending on what you want to know about it, right? If you want to know where it's at, then it's going to behave like a particle, but you can't know anything about its wave-like nature. If you want to know the interference pattern it produces, right, then it's going to behave like a wave, but you can't know where it's at. Okay, and that's kind of like where we come to, and what people have such problems with respect to quantum mechanics, is that there is no, like, you can't get better, right? You can't be like, oh, but we're going to trick it one day, and we're going to figure out where it's going and be able to measure the interference pattern. It's impossible, right? This is what essentially is told to us by the uncertainty principle, as well as the fact that these are complementary properties, right? The more you know about one, the less you can possibly know about the other, and that is what quantum mechanics really gives us with respect to the electron, which is unfortunate for some people. Okay, so again, these things were complementary properties. So this is a very particular term with respect to quantum mechanics. With complementary properties in quantum mechanics, again, the more you know about one, the less you can possibly know about the other, right? So with our little diffraction experiment, when we knew its position, we didn't get to see the interference pattern. But when we saw the interference pattern, we had no clue where the electron was actually at, okay? And so the wave nature, the particle nature, these are the two complementary properties, and their actual physical phenomena versus the interference pattern versus the position are what we mean by these properties, these complementary properties, okay? Okay, so this trade-off, this tit for tat with respect to these complementary properties are quantified or kind of formalized via what we call the Heisenberg uncertainty principle. Okay, so in the uncertainty principle, what they tell us is that position, which is part of the particle-like nature of the electron, and velocity, which is part of the wave-like nature of the electron. These are our two complementary properties that we deal with in the Heisenberg uncertainty principle, right? And so what it states is that the uncertainty in position, and that's what this delta x means, it's not change in, but instead is uncertainty. So uncertainty in position times the mass of the electron times the uncertainty in velocity. So this is uncertainty in velocity are greater than or equal to some finite number, right? And so what this is really telling you is the smaller the uncertainty in position, so the more we know about the position of the electron, the larger the uncertainty in velocity, so the less we can possibly know about its velocity, right? The more we know about the particle-like nature, the less we can know about its wave-like nature, and vice versa. And so again, these guys are kind of inversely proportional to one another. The more you know about one, the less you can know about the other. Again, the position of the electron is part of its particle-like nature, whereas the velocity of the electron is part of its wave-like nature. And that is what we're kind of left with. This is going to determine how we imagine these electrons, and not imagine them, but how we envision them occupying the region of the atom around the nucleus from here on out. Okay, so unfortunately, kind of the trade-off in all of this is that energy is essentially related to velocity, which is part of the wave-like nature of the electron. And we know lots and lots and lots about energies of electrons, and so kind of with respect to that, that means that we can't know very much about the position of the electron. Okay, so again, kinetic energy, which is what we're talking about, energies of this electron. This is related to the velocity of the electron via just the equation for kinetic energy. Velocity is part of the wave-like nature of the electron. We know lots about these guys. We know lots about energies and velocities. And so because of that, we cannot know much about its position. And so Unfortunately, that's what we're left with respect to quantum mechanics. So what does that mean? Okay, so this kind of leads us into the Schrodinger equation, which is developed or was developed by this guy named Erwin Schrodinger back at the, time that people were doing all of this stuff. So what the Schrodinger equation does is it, for the first time, treats the electron as a wave, as purely a wave, okay? And so you don't need to know about this equation that much, right? The only thing you need to know is what we're going to get out of it, right? So what we're going to get out of this equation, let me start by saying what this equation is trying to state. So this part of the equation is essentially looking at the potential and kinetic energies of the electron, and it's equaling the total energy of the electron, okay? What this guy is, this little Greek letter psi, what this is what is called a wave function. Okay, so this is just like your normal functions like fx or something like that, right? These are normal functions, but with respect to the Schrodinger equation, these guys, these wave functions, are going to be our solutions to this equation, like solving for x or something like that. But with respect to this guy, we're going to get many different solutions. So many values of psi will actually satisfy this equation. Okay, so what's coming out of this is psi, and what this is trying to represent is the overall position of the electron. Okay, so position of the electron. Psi itself, all these different solving, or all these different psis that we can get, has no physical meaning, but when we take psi and we square it, what this ends up being is the probability. So probability of finding the electron in a given region of space, okay, around the nucleus of the atom. So we're always going back to the atom. This is not just some lone electron living off in nowhere land, okay? Okay, so this guy, psi squared, again, we have many different possible solutions for this, and what we're going to call these are orbitals. So this is kind of a misnomer. It goes back to this idea behind the Bohr radius and like this electron orbiting. Again, it's just kind of stuck. So these psi squares, these probability distributions, we're going to call orbitals. Okay, so again, there are many different possible wave functions, many different possible solutions to the Schrodinger equation. The wave function itself has no physical meaning, but the wave function squared is going to give us our probability distribution of finding the electron in a given region of space around the nucleus, okay? So because there are many different solutions to psi, that means that we're going to have many different possible orbitals. All of these orbitals are going to be characterized by three separate quantum numbers, okay? So first one is what we call principal quantum number. The second is angular momentum quantum number, and the third is the magnetic quantum number. And it's going to be these combinations of what we call N, the principal quantum number, L, the angular momentum quantum number, and M sub L, right? So this is an M with a subscript L. These guys are going to characterize each individual orbital that we're talking about, okay? Each individual probability distribution of finding the electron in a given region of space. So right now, I know this has, like, you're like, what? I don't get it. It's okay. Hopefully I'll try to make sense as we actually start to deal with various values of N, L, and M sub L. Okay, so we're going to start by first talking about N, the principal quantum number, and what it is essentially going to specify about the orbital. Okay, so N, again, called the principal quantum number, what it is going to tell us about the orbital is it's going to give us the energy of the orbital, right? So overall energy of the orbital, as well as the overall size. And I don't mention this up here. So this will also give us an idea about the size of the orbital. Okay, so with all of these quantum numbers, they are all going to be integer values, right? So it has to be a 1, a 2, a 3, or 4 integer values, right? They're all going to have rules with respect to what number it can actually be. So for N, our rule is that N can be any integer greater or equal to 1, right? So N can equal 1, it can equal 2, it can equal 3, and so on. n cannot equal 0 or anything negative, right? So anything negative is forbidden with respect to n. So these guys do not count. So the only values that n can take on are 1, and then in theory I think out to infinity or something like that, but we don't usually get out there. Okay, so again, that's the rule with respect to n, the values that it can take on. Number 2, another thing to note, is that the larger the value of n, the more energy the orbital has. Also, the larger the value of n, the larger the orbital. Okay, so the bigger n, the more energy, the bigger n, the larger. Okay, and then one more thing. So what this n kind of represents, if we go back to the idea behind the Bohr model of the hydrogen atom, was those radii, those fixed radii, right? So instead of drawing them like Bohr did, what we're going to start to draw them more like is like this nice little energy diagram, as we have energy here on our y-axis, and we're increasing our principal quantum number here. These were essentially those Bohr radii. Okay, so n equal 1 was the one closest to the nucleus, n equal 2 was the next one out, and so on and so forth. So again, as n gets bigger, we're going to increase in energy, right? We're going to also increase in size. Also, as we increase n, what we're going to see is the energy spacing between the orbitals is going to get smaller, right? So for example, going from n equal 1 to n equal 2, we're going to get a certain energy spacing here. As we move up to n equal 3, that energy spacing between the two levels gets smaller, and it's going to continuously get smaller as we continue to move out, okay? So n can be any integer value from 1 to, I think, infinity. N tells you about the energy and the overall size of the orbital. The larger n, the bigger the orbital, the more energy. And then as we increase n, the difference or the distance between the orbitals is going to get smaller. The energy distance, I guess, between the orbitals is going to get smaller. Okay, so again, principal quantum number. Number 2, with respect to our quantum numbers, is the angular momentum quantum number. So we give the angular momentum quantum number this little denotation by the letter L. So what is L going to tell us? What is the angular momentum quantum number? So overall, what L gives you is the shape of the orbital. Okay, so each orbital is going to have its own characteristic probability distribution or shape, right? And so L is going to tell you what that shape is, essentially. So again, there are rules with respect to the values L can take on. So it can have integer values from 0 all the way up to n minus 1. Important to note here that L depends on n, right? So whatever n you have is going to tell you what values of L are possible. And then also important to note is that I think at the time people thought it would be confusing because, right, we're using n's with 1, 2, 3. If we were using L's, with 1, 2, 3, or whatever we're going to be using, so on and so forth, then when we talk about an orbital, we would call it the 1, 1 orbital or the 1, 2 orbital. So people thought that would be confusing, and rightly so, it would be confusing. And so because of that, each number for L is going to be essentially represented by a letter, okay? So, and I'll tell you which numbers represent which letters in a second. So there are, for us and our intensive purposes, there are 4 orbitals or 4 letters that we need to know. So the first one is the s orbital, p orbital, d, and f, and these correlate to L values. So L values here of 0 for the s orbitals, 1 for the p, 2 for the d, and then 3 for the f's. Okay, so L. L gives you the shape, and then it depends on n, and it can have integer values from 0 all the way up to n minus 1. Okay, so let's actually do a problem that utilizes this. Okay, so for example, let's say we have an orbital, and that orbital has n equal to 4 as the principal quantum number. So what are the possible values of L? So remember that L can be any value from 0 all the way up to n minus 1, right? So L can be 0, it could be 1, it could be 2, and then if we have n minus 1 here, that's 4 minus 1, which gives us 3, so that is the last one that we can be, right? So L can be 0, 1, 2, 3, which is n minus 1. So there are 4 possible values for L when n is equal to 4. Okay, so again, with these letter values, or these number values, L equal to 0, this is our s orbital, our p, our d, our f. So this would be, correct answer here would be D, and this would be S, P, D, and F.